Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 19th lecture on the Euler-Lagrange equation. So to get us started, I've got a video, this is kind of a fun video of a team of robots that are running and jumping and dancing. And I like this video for today's lecture because it's all about dynamics. Now, dynamics is a relationship between the torques and forces you apply to a system and the way that system moves. Maybe take your own arm as an example and think about the different torques you apply to your elbow and how that causes your hand to move around in space. That's an example of dynamics. Now, in these videos, I've got systems that have many different links, many different joints, and then all the actuators that are powering those different joints and causing those links to move. And what I want to figure out is, how do I pick the torques for those joints that cause my system to move in the way I want it to move? So if I want my system to dance or to run or to jump, what torques should I have at the joints for that system? Well, that's something I need to understand my dynamics to answer. And so in today's lecture, we're going to start talking about dynamics with something called the Euler-Lagrange equation. So I'll explain what is that Euler-Lagrange equation, and then what happens when you apply the Euler-Lagrange equation to robot arms. All right, so let's get started with a simple example. I want to find the equation of motion, i.e. the dynamics of a point mass. And I'm showing you a point mass right here. The mass is going to be m, and it's at position theta, where moving upwards is a positive change in position. I've also got a force F that's pushing this mass upwards, and I've got the effect of gravity that's pulling it back down. So I've got mg that's pulling this mass back down. So maybe you could take a second, use Newton's second law, and come up with an equation of motion or dynamics for this simple system. Probably you came up with something like the equation you see right here. Now, with Newton's second law, I know F equals ma. So here's my ma, or in this case, m theta double dot. That's the mass times the acceleration for my point mass. Good. On the other side, I've got the sum of the forces applied to this point mass. I've got F pushing it up, and then I've got mg pulling it down, and that's why I've got the minus sign right here. So overall, I was able to look at my diagram and apply Newton's second law, and I could pretty easily come up with this equation of motion. The question I have for you, though, is how are you going to scale this up? So sure, I can do that for a simple point mass, but for my serial robot arm with all of its joints and links and moving in our three-dimensional world, how am I going to come up with its dynamics? So to find the dynamics for more complex systems, one solution is the Euler-Lagrange equation. Now, I like the Euler-Lagrange equation because it has some connections back to kinetic and potential energy. And the main idea is I'm going to use the kinetic and potential energy of a system to derive that system's dynamics. And we combine them using something called the Lagrangian. So the Lagrangian is the kinetic energy minus the potential energy. That's what you're seeing in this equation. Here, K is my kinetic energy, and that depends on both my joint position theta and my joint velocity theta dot. So here's my kinetic energy. And then on the right side, I've got my potential energy, and that just depends on my joint position theta. So here's my potential energy. And the idea with the Lagrangian is I'm going to say L, my Lagrangian, is equal to K minus P. All of these are going to be energy terms. They will all be scalars when you implement them. I want to mention that for our robot arms, the kinetic energy is going to be caused by motion. So you might think about how that arm's moving in space, and maybe the joint velocities and the way that those joint velocities can cause the energy due to motion. Now for our robot arms, the potential energy is going to be caused by gravity. So I'll be thinking about the height of the system and how gravity is pulling that system back down, and that's going to be the source for my potential energy. So for my kinetic energy, I'm thinking about my joint velocities and my motion. For my potential energy, I'm thinking about the system's height and the effect of gravity. All right, so the key idea is I'm going to take this Lagrangian, and I can use the Euler-Lagrange equation to convert that into an equation of motion, to convert it into my system's dynamics. And here's that Euler-Lagrange equation. I've got F, which is the output. Again, I'm thinking about this just for our simple point mass, where I was looking at a scalar, like just thinking about the 1 degree of freedom system. And so F would just be the force that I'm applying to that point mass. Then my first term is going to be d dt times the partial derivative of my Lagrangian with respect to theta dot. So again, I'll take the partial derivative of the Lagrangian with respect to my velocity, and then take the time derivative of the result, and that will be my first term. My second term is the partial derivative of the Lagrangian with respect to position, and that's going to be your second term. And you just do the subtraction right here, and that's going to give you your Euler-Lagrange equation. That will give you the dynamics for your system. So kind of a mouthful to talk through, but a bit more easy when we start applying it. So let's go through an example. So we're going to use the Euler-Lagrange equation to derive the dynamics for this point mass. Now, you might say, I've already found the dynamics of this point mass, and you have. The idea is, can we see if we can get the same answer if we use the Euler-Lagrange equation? So let's get started by finding the kinetic and the potential energy for this system that we've seen before. As a reminder, your kinetic energy, that's going to be energy due to motion, and your potential energy, that's going to be energy due to the height of the system and the effect of gravity. Maybe from physics, you remember something like 1/2 mv squared for kinetic, and for potential, you might think about maybe mgh. Well, if you just convert those equations to the system, you'll end up with your Lagrangian. Here, my kinetic energy is 1/2 m theta dot squared. It's the exact same as 1/2 mv squared. It's just here my velocity is theta dot. And then my potential energy is mg theta. Again, the exact same as mgh, except for here the height is just going to be theta. So I've got my kinetic energy minus my potential energy, and that's my Lagrangian. As a reminder, these are scalar values. All right, now I can apply the Euler-Lagrange equation. Let's practice using this equation to see how it works. I've written down some orders here to make sure you do the steps in the right order. For this first term, make sure you take the partial derivative first and then take the time derivative. So the order here is important. So I'll be looking at my Lagrangian. I'll take the partial derivative with respect to my joint velocity, and then take the time derivative of the result. If you work through that, you'll get m theta double dot. Now here, for my second term, I'm going to take the partial derivative with respect to theta. If I do that, I'll get negative mg. Now remember you've got a minus sign right here, and you're subtracting another minus sign. So if you work through the whole thing, you'll have f is equal to m theta double dot plus mg. And this result matches what we previously found using Newton's second law. So we're still getting the same dynamics, we just have a new way to find them. And the advantage of this method is that it will scale well as my system becomes more complicated, like what we see for serial robot arms. All right, so let's try using these dynamics. And I just want to show you kind of one simulation. On the left side, I've got my point mass, and here's the equation we found. And then I've got two different plots. In this first plot, I'm showing time, first position. In the second plot, I'm showing you time, first force. And what I've done is I'm plotting the force F I'm applying, and I'm going to start off by applying a constant force of 10 newtons. I can then see how my system moves, and I notice that, okay, if I apply that force, my position increases. At some point, I reduce the amount of force I apply, my system starts falling, and then I increase my force to kind of stabilize the position of the system. The exact plots you're seeing aren't particularly important. What I want to emphasize is that once I understand the dynamics, I now have a way to map between the forces I apply and the way the system moves. And this is a really important thing to understand, because now I know, all right, if I apply these torques of my actuators, this is how my system will move in space. Again, thinking about my robot arm, I now understand how I can choose different joint torques to make my system run or jump or dance or whatever it is that you want your system to do. All right, so we've talked about the Euler-Lagrange equation, and we applied it to that pretty simple point mass. But what happens when I apply the Euler-Lagrange equation to robot arms? The good news is many people have done that. And we've realized that when we apply the Euler-Lagrange equation to robot arms, we get a standard form of solution. And so we've kind of done the hard work of finding that standard form of solution, and I've written it for you right here. So the dynamics of a serial robot arm with n different joints can be written as what you see. Tau is equal to m theta double dot plus c theta dot plus g. I'm going to explain what each of those terms mean. Here, tau, that's going to be your vector of joint torques. So again, if your robot has n joints, it'll be an n by 1 vector. And it's totally fine if some of those torques are actually forces because they're prismatic joints. Again, just think about tau as your vector of joint forces / torques. Then theta, that you see in a couple different places, that's going to be your n by 1 joint position. Theta dot, that'll be the n by 1 joint velocity. And then theta double dot, that'll be your n by 1 joint acceleration. So here's my acceleration, here's my velocity. Right, and those are all things that I could measure. For position, I can measure that using encoders. My velocity, maybe I have to take a derivative. And acceleration, that's a little bit trickier to measure, but we can try to come up with some estimate of the velocity for our robot arm. The terms that are kind of new and we'll have to think about a bit more are m, c, and g. So M, that's going to be my mass matrix. It's going to be an n by n matrix that captures the mass of my overall multi-body robot arm. C, that's going to be the Coriolis matrix. It's also going to be n by n, a square matrix. And then G, that's going to be your gravity vector. So that'll be an n by 1 vector. And when you do the multiplication here, you're going to end up with an n by 1 vector for joint torques. I'd point out that M and C, these first two terms, these stem from the kinetic energy of your robot arm. And G, this is going to stem from the potential energy of your robot arm. Now, again, the dynamics you're seeing right here, they come from applying the Euler-Lagrange equation to the kinetic and potential energy for serial robot arms. It's just, we've gone through this process many times and we recognize that we can write this in some sort of standardized form. All right, so I've introduced the Euler-Lagrange equation and I've explained what happens when we apply that equation to robot arms. If you want to practice the Euler-Lagrange equation a bit more, I encourage you to check out the practice set. You can see it in the discussion or the pinned comment. The first page has the questions and the following pages have the answers. One question you might have is, what the heck is M, C, and G? How do I find this mass matrix, this Coriolis matrix, and this gravity vector? And that's exactly what we're going to start talking about in our next video. So I look forward to seeing you there.